Friends, good morning to everyone. We were dealing with the side reactions that occurs in peptide synthesis due to protonation and proton abstraction. Today's subject of discussion is side reactions that leads to alkylation by intramolecular rearrangement. For example, when I have a benzyl protected tyrosine, when I deprotect it, I use trifluoroacetic acid. The trifluoroacetic acid has the OH, which is having lone pair of electrons, and this is the positive center benzyl carbon. As adjacent to it, there is an electron withdrawing group. This is electron rich and this is electron deficient. That's why lone pair of electrons attacks on this positive center and it has to maintain its tetravalency. That's why that electrons are moved on to the oxygen to give rise to oxygen anion of tyrosine and benzyl ester of trifluoroacetate. This trifluoroacetate benzyl carbon is a positive center. The excess electrons on this oxygen anion makes it unstable. That's why to regain its stability, these excess electrons are moved towards the next carbon. And carbon has to maintain its tetravalency. That's why pi electrons moves towards to the next carbon. And it gives rise to carbene ion. This carbene ion attacks on the positive center of the benzyl ester of trifluoroacetate and it gives rise to removal of this trifluoroacetate ion, giving rise to again orthobenzyl substituted tyrosine. Alkylation by R-alkyl group of this benzene ring occurred by this intramolecular rearrangement. The benzyl and the oxygen has got shifted to carbon on the benzene system. The carbocations are generally formed during the removal of the protecting group from amino acid in the presence of the acid like trifluoroacetic acid. This acts as a center for a nucleophile like carbene ion which is generated and thus the rearrangement occurs to give the alkylated amino acid. The meta position alkylation won't take place because of the bulkiness of the group present at the para position. That's why when we deprotect it, we have to deprotect carefully such that this side reaction should not occur. Side reaction can also occur due to overactivation, overreaction. During the coupling of amino acids to form peptides using the coupling agent like DCC, dicyclohexyl carbodiamides, a subtle intermediate O-acyl isourea is formed. This O-acyl isourea can react with the other amino acid to form the peptide bond. But however, this O-acyl isourea is also prone to form symmetrical anhydrides and azalactones. Also, it can rearrange to give N-acyl urea. These are the byproducts formed during this coupling with DCC. For example, this occurs in acylated amino acids especially. An acylated amino acid I take and treat with carbodiamide. The lone pair of electrons on the oxygen attacks on the carbon, which is the positive center, and the pi electrons moves onto the nitrogen to give rise to O-acyl isourea. This O-acyl isourea, it can react with other amino acid as this is an easy bulky living group that can attack and a peptide bond can be formed. But there is competing reaction for these two. What are those? Instead of before the amino group of the amino acid getting attacked on the carbonyl group, the carbon anil and oxygen bond breaks and these electrons moves and it gives rise to isourea and it gives rise to a positive carbonyl. This positive carbonyl which is formed before the amine attacks, the acyl group which is attached to the amino which is nearer to this carbonyl center, the pi electrons moves towards the oxygen due to the electromeric effect of the positive center which acts as an electrophile. This O minus oxygen anion combines with this positive center and it gives rise to azalactone. Azalactone is one of the intermediate which is formed. Though it can be reversed, but what it gives is not the desired peptide. This can also undergo another reaction. The O-acyl isourea can react with another acylated amino acid. This acylated amino acid can compete with the amino acid which is incoming. The OH lone pair of electrons attacks on the carbonyl carbon of the O-acyl isourea and this gets kicked off to give urea N, N alkylated urea and it gives rise to symmetric anhydrides. Symmetric anhydride is the another byproduct which can be formed or it can undergo rearrangement. The pi electrons moves towards nitrogen moving towards the electronegativity of the nitrogen giving rise to nitrogen anion. And this nitrogen anion which is formed which is unstable to maintain its stability, this excess electrons it passes on to this carbonyl carbon. Once the bond between this carbonyl carbon and the nitrogen is formed, the bond between the carbon and oxygen gets broken up and it gives rise to N-acyl urea. That's why when we do coupling reaction of acylated amino acids, these many possibilities are there. Hence, we should optimize the reaction condition to avoid this azolactone, symmetric anhydrides and N-acyl urea formation as byproducts. The overactivation can also occur in case of indole and imidazole containing amino acids like tryptophan and histidine. When it reacts with carbodiamide, it gives carbodiamide substituted guanidines. I take tryptophan and I treat with dicyclohexyl carbodiamide. The OH lone pair of electrons of carboxylic acid group should attack over here to give the activated ester. But however, there is the NH group in the indole ring system present in the tryptophan, which has lone pair of electrons. This competes with the lone pair of electrons of the oxygen COOH, and the lone pair of electrons in the nitrogen can get donated onto this carbon of carbodiamide, and the pi electrons moves onto the nitrogen to give rise to guanidine substituted tryptophan, rather than giving the activated carboxylic ester of the tryptophan. Here इधर एक ही कृष्णा है, carbodiamide is krishna, OH of COH and NH of indole are राधास. एक कृष्णा के लिए दो राधा कॉम्पीट कर रहा है एंड दूसरा राधा समटाइम्स विन्स. Similar to this, in histidine, which has the nitrogen with lone pair of electrons, can react with carbodiamide and it can give rise to guanidine substituted histidine. These are the side reaction. Why it is overactivated? Because there is OH and also NH. Both compete with each other for the common carbodiamide. That's why these byproducts can also occur along with the activated ester of tryptophan or histidine. However, this guanidine side reaction can be reversed when we treat with methanol in the presence of an acid. Acid catalyzed methanolysis. OH lone pair of electrons attack on this carbon of guanidine and the bond between the carbon and nitrogen breaks and it can be liberated. Same will be the case with tryptophan. And that's why even if it is formed, we can work it up, hydrolyze it, and we can recover the starting material. And this is how we can prevent the formed guanidine substituted histidines or tryptophans. These are the few side reactions which occurs due to the overactivation. In the coming presentation, I'll be dealing with the side reactions of individual amino acids. Till then, have a nice day. Thank you.